Hey everybody, wanted to go through these couple problems here because they were fun ones, but definitely some challenge. Feel free to fast forward, jump ahead, zoom around, whatever you need to do. Um, but yeah, the answers were provided, so obviously you can double check. You could have double checked that, so if there's just one you wanted to check, I'm going to work through all four of these, numbers 2 and 3 first. So number 2, it's sort of this scenario different than we have discussed, but we have a point moving on this graph. And so I don't think I even necessarily need to sketch this one so much because I'm going to be able to make sense of this because the equation is already given to me. So they're saying what we know is we know this equation. It's on the graph xy equals 24. And at the moment, we know that dy dt, because you see it's at 2 units per second, not 2 units per x. So dy dt, the y is increasing at a rate at 2 units per second. And what we're trying to find is the x dt. How is that point changing with regard to x at that moment? So you can also use this method to analyze instantaneous motion in these abstract scenarios. So one thing that I thought was maybe interesting, they wanted us to find that when y is equal to 3, right? And this is also, that's at when y equals 3. One thing that might be helpful here, and we're going to see that it is going to be necessary, is that well, if we know at the moment when y equals 3, since x times y equals 24, well, x has to be 8 at that moment. That's going to be helpful, I found in this scenario. And I rewrote it to derive as I just divided the x over, because then I could think of it as x to the negative first, which is nice for me to power rule. So my left side, once I derive, let me be more thorough here. So I'm going to take the derivative with respect to t of y, and the derivative with respect to t of the right side too, also. So here I'll just get dy dt. Here I could put the 24 constant in front. I would derive this to get negative 1 times x to the negative second, then chain rule it dx dt. So I could smush some of this together to give me, let me switch colors. So dy dt equals negative 24 over x squared dx dt. So we want to find dx dt. What we know is that, so if you didn't find what x was already, you would maybe now think, oh, well, I have an x here. I can't solve for dx dt until I plug that in. But we did that because I figured that out when first time I did it on my own. Dy dt is 2, so we just plug that 2 in. Negative 24 over x squared, that'll be 64 dx dt. I think if I take an 8 out of both of these, I would get negative 3 over 8 times dx dt. And then to solve for dx dt, I multiply it by the reciprocal, which would be negative 8/3, so I get negative 16 over 3. That's what dx dt equals. So let's think about that. So that was units per second. So that's how the x is moving. The x is moving in the negative direction at negative 16 thirds units per second. And that's what the answer key told us. That's good. So that one is on a graph. We would see that if I pull this graph over here, let me show you. Let me ignore this. But at that moment, she said when, so they gave us the condition that the y was increasing, so it makes sense that the y was increasing, that the x is decreasing. And it tells us the specific value at which that would be, because if this is going up, well, it's got to go to the left, which would mean the x value is decreasing. Alright, let's look at this next one with this funky drawing here that was provided by the Drexel website. So, a boat is being pulled towards a dock by a rope, and this was a fun one for me to think about. Hopefully you enjoyed it too. So this rope is being pulled, it's attached to the bow of a boat, the bow of a boat, is being pulled through a pulley which is 4 feet above the dock. So he's pulling on this, I guess it's kind of a pulley here, he's pulling that pulley, I guess maybe that's where it comes from. So the rope's being pulled at a constant rate of 2 feet per second. So this rope is being pulled at 2 feet per second. So if I understand correctly, then this is moving this way on the water, but the rope is going to be getting pulled, so it's going to be getting 2 feet shorter per second. So what do I know? I guess that's a piece right there. I know that the change of the rope over time is negative 2 feet per second. Okay. How fast is the distance? So this is why you may have seen I had this labeled as the distance between the boat and the dock changing. So we want to find the derivative of the, how is the distance, so I did dd for distance. I don't know what you would have chosen, but what is, find ddt when the boat is, when the distance is 10 feet from the dock. So, okay, let's see what we can figure out here. Well, it looks like this is going to be, is it called the Pythagorean Theorem? I don't know, I'm getting fatigued over here, if I can be honest. So we got d squared plus, well, this is staying at 4 feet, if I correctly, so 4 squared is 16 equals the rope squared. Okay, let's now derive with respect to time on both sides. Okay, so this would give me 2d, but then I need a chain rule it since dd dt. This would just disappear to 16. And this would give me 2r dr dt. Okay, so I know d. Oh, it's another part where at the moment when this is 10 and this is 4, I could figure out what this is by the Pythagorean theorem. So that'll be 10 squared plus 4 squared equals r squared. That'll be 116. So r would just be root 116. So now we could plug in some of these mamma jammas. So we know that d is 10, so this would be 20. So we want to find d dt, okay. We know that r is root 116 and dr dt is negative 2. Okay, so it'd be negative 4 and then root 116. So I just divide by the 20 and I think we've got it, right? Oh, negative 4 root 116 over 20. Cancel that. 4 goes into 25 times, so it'll be, so I think dd dt, or the rope, or the distance, I should say the distance between the boat and the dock is getting smaller at a rate of negative root 116 over 5 is what I had when I changed that to 20. And I believe it was in feet per second. So the rope is, or the distance is getting, so I guess this would be square root of 116 would be between 10 and 11. So It'd be a little bit more than 2 feet per second, if I'm not mistaken. Number 6 was a bit of a wild one also, and so let's draw this one out. We got another one of these wall situations. So a wall, then you got a plank, funky plank there, but we'll go with it. And then I got the ground there, green. Okay, so the bottom plank is being pushed towards the wall, so I would call this maybe G for ground, and we call this W for wall. And then we get the plank. They told us the plank is 24 feet, so that's not going to change, the plank. But they're telling us that the plank is being pushed towards the wall. Okay, so we know at a constant rate of 3 feet per minute. So this is going to be getting smaller. So over time, that ground distance is getting smaller at negative 3 feet per minute. Oh, acute angle. So we got the acute angle the plank makes with the ground changing at the instant. How fast is that, man? Is that angle changing at the instant when? So find the theta dt when the plank is 12 feet from the wall, or G equals 12 in our diagram. Wow, are you for serious? Okay, let's see. Well, really, they didn't really say anything about the wall, so we're really trying to relate the angle and to the ground. We have info in 24. So, if I'm not mistaken, so kato, yes, I think it would be cosine would measure or relate the G to the 24. So we could say the cosine of theta equals G over 24. That's a correct equation. Correct me if I'm wrong. Or you can, you're just watching the video. Ha ha! Well, always leave a comment, but let's keep it rolling. Sorry this video is going on a little bit long, but okay, so we could derive both sides. Let's just see what happens. And then we'll derive the right side. So the derivative of cosine is negative sine, right? So it'd be negative sine theta. Then we need to chain rule it since it's really a function within a function because we're deriving with regard to time. And then we, here we would just get, I could just pull the 124 over 124, and then it would be dg dt. Okay. So the thing here is that we haven't used this g equals 12 yet. And I think what I'm now noticing is that we're going to need to know what theta is at that moment. And they told us when this is 12, oh, so if we go back to our original equation, the cosine of theta at that moment is 12 over 24, or 1/2. So do you remember what angle has a cos of 1/2? I believe it's on my unit circle. Let me drop it right here. We've got, pi over 3 is when we have a cosine value of 1/2, or 60 degrees, if you like thinking in degrees. And then you could do this in your calculator, and it would give you pi over 3. 60 degrees. Okay, so negative sign, we can now plug that in because that's the theta at that moment, the measure of the angle. We want to find the d theta dt, so we still don't know that. We got the 1 over 24, and then we got dg dt was given to us at negative 3. Whew. This is funsies, McFunderson. Ha ha! Well, we go back and find out the sine of pi over 3 at that same moment, root 3 over 2. So we got negative that, which is negative root 3 over 2. d theta dt, which is what we'll try to find.